Yeah. Cool. Okay. Hi everyone. I think we're going to start in a few minutes. I'd just like to point out that the toilets are to the left at the back there. There's a little kitchenette, you can get a glass of water or anything like that. All the fire exits are signposted. The nearest ones are through where you came in and the far end there. And I think there's one that way as well. Thanks for coming to our second Southwest Futurists. We've got a hashtag. Tonight's all about quantum computing. I know this much about the subject, so I'm really excited to hear from these guys from Bristol University who are doing their PhDs.
No.
But don't worry, they'll be talking about what they do, and that'll be fantastic. So do tweet along and ask. Think about questions you should ask them at the end of each talk. We'll have a little bit of time for Q&A, and then at the end we can all go to the bar, and if you can stick around we can ask them more questions and have a general discussion. We're live streaming, so please don't swear too much, and you can find it on YouTube at the address afterwards. So thanks very much. Cool.
Thanks, Ben. Okay, so I guess standing here is good, right, for the camera?
Yeah, don't worry about it.
Great. Okay, so yeah, let's get started. So firstly, thank you all very much for coming along this evening. It's really great to see so many people here interested in this stuff. Indeed, my name is Ashley Montanaro. I'm from University of Bristol, from the School of Mathematics there. And this evening I want to tell you about quantum computing, a little bit about how it works and what its applications are, and also why I think it's such an exciting field, both now and kind of for the future as well. So before that, I think I should probably start by introducing myself a bit, just so you get an idea where I'm coming from. So I've been working in the field of quantum computing for over a decade now, just like scarily. And before that, my background was actually a bit different. I was a software engineer working on software for mobile phones. Then I came to Bristol in 2004 to do my PhD. After that, I moved around a bit, Bristol and Cambridge, and now I'm back in Bristol as a lecturer in the School of Mathematics there, and also a research fellow. So within quantum computing, my research more specifically is theoretical. So I'm trying to understand what quantum computers can do, what they can't do, whether we should actually bother trying to build one, that kind of thing. And then later on you'll be hearing from Jack, who's an experimentalist who is actually trying to build one. So we'll kind of have a mix of these two things. Okay, let's get started. So what is a quantum computer? So a quantum computer is a machine which uses the principles of quantum mechanics to try to do things which are impossible for any standard computer that's based only on the laws of classical physics, so like Newtonian physics, if you like. And quantum mechanics turns out to enable totally different sort of modes of information processing, which are just not accessible to standard computers that we might have now on our desks or in our pockets or whatever like that. And another answer to what is a quantum computer is this slide, really, because these four pictures here, which I guess this pointer isn't going to work, but these four pictures are all small-scale quantum computing experiments from various different groups worldwide. So these are experiments that exist now. These are all sort of relatively recent things. And they're based around varying different technologies. The one on the top left from the University of Bristol is based around photonics, so it has a circuit within it that operates on photons or particles of light. The one on the top right, which is from UCSB, the university in the US, and also Google, is a superconducting circuit that has 4 quantum bits or qubits in the middle that you can see there. They're the sort of wiggly, sort of rectangular shaped things there in a diamond pattern. The one on the bottom left is from IBM, and that's also a superconducting circuit, and the one on the bottom right is from the University of Oxford, and that one works using some kind of trapped ions. So these things exist, but at the moment they're small scale, but that doesn't stop us from trying to figure out what we could do with a large-scale quantum computer, what it would enable us to achieve. And that, I guess, is what this talk is really about. Okay, so I should start out by just introducing a few of the basic concepts behind quantum mechanics and why it's kind of interesting and different to standard physics that we're familiar with. And perhaps the easiest way of doing this is looking at a very simple quantum system, which is a photon, a light particle. So this photon, it just kind of goes along in a line like this, if we kind of fire it out of a laser or something like this. And one thing we might do to it is stick a mirror in its path. And if we stick a mirror at a 45-degree angle like this, the photon's going to bounce off the mirror, as you would expect. So it kind of goes along to the right, and it bounces off and goes upwards. So this is pretty much what we would expect. But things get a bit more interesting if we change the mirror, so it's not completely reflective, but it's only partly reflective. So it has, let's say, a 50% probability of reflecting the photon, so it goes upwards, and a 50% probability of letting the photon pass through. So it just goes through the mirror. Now, what we might sort of naturally expect to happen here is that with 50% probability, indeed, the photon goes up, and with 50% probability, the photon goes to the right. And it does one or other of these things, depending on whether it happens to pass through the mirror or be reflected by the mirror. But in fact, quantum mechanics says that something different happens in this situation. The photon is actually simultaneously reflected and transmitted through the mirror. So rather than having a 50% probability of going either way, it becomes a state which is somehow both of these directions at the same time. So it's both going up and going right simultaneously. And this quantum phenomenon is known as superposition. So you might immediately complain, well, maybe this is just some kind of semantics here, because maybe when I draw it like this, what I really mean is that what's happened on an underlying level is that the photon's either gone up or gone right, and this is just a way of expressing that. But in fact, these two cases are fundamentally different, the kind of quantum case and the non-quantum case. And there's even an experiment right here at the front which will enable you to see that, I guess, a bit later on. You can experimentally verify that this superposition phenomenon does happen, which is kind of amazing. Now, it's maybe already kind of natural to think about how we could use this for information processing, this phenomenon. And one way we can think about this is that the path of the photon can be seen as encoding a bit of information, like one bit, a 0 or 1. And for example, we could say if the photon goes up, that encodes a 0. If the photon goes right, that encodes a 1. And then we could have some kind of measuring device that reads out whether it's a 0 or a 1 based on which direction the photon's gone. Now, if we have this photon in a superposition of both 0 and 1, that's with this half reflective mirror here, then that means that if we perform some computation on this bit of information, rather than performing the computation on 0 or on 1, we've performed it on both 0 and 1 simultaneously, in some sense. So this kind of immediately makes us think, well, maybe this allows us to compute on multiple inputs at once. And this might give us some kind of power which isn't accessible to a standard computer that can only compute on either the 0 or the 1. And even more than this, we have this kind of exponential doubling effect with this superposition, because if we have n photons, some sort of large n, then this gives us 2 to the n different possible states that they can all be in. Each one could either go up or it could go right. So that's 2 states, and then if we have n photons, there's 2 to the n different possibilities. And if the photons are all in superposition, that means we have a superposition over 2 to the n different states. So this seems that we can compute perhaps on exponentially many different inputs at once. And in fact, this does indeed turn out to be the case, though one has to be quite careful and quite clever to actually come up with quantum algorithms that exploit this effect and to do things that we can't do classically. So just to mention kind of some of the key ingredients of quantum mechanics that make it so different from our everyday life, the first one I already mentioned is superposition. And this is kind of a general phenomenon. So if we have some system that can be in state A or state B, it can be in some superposition or some mixture of these two different states. And the thing that's particularly interesting is that if we measure this system, then we either see A or we see B. We don't see some mixture of the two things, and we might see A or B kind of probabilistically, with some probability we see A and with some probability we see B. So we never see the whole kind of superposition at once, which is why it's kind of hard to use this superposition effect for information processing. Okay, and the second interesting thing is that when we do this measurement and we see either A or B, then if we keep doing the same measurement, then we keep getting the same results. If we saw A the first time, then we keep seeing A again and again and again. So this, again, is something we don't necessarily see in our everyday lives, this effect. More interesting still, there's this phenomenon which is talked about a lot, known as entanglement, which, roughly speaking, says that there are systems that have multiple parts in them, so a system of kind of n photons or something like this, and that can't be described only in terms of their constituent parts. So there's no way in which we can split up the system just in terms of its individual elements. To understand the system fully, we need to understand it kind of as a whole, not in terms of its separate things. And this can even be the case for systems of particles that are separated a long way away from each other physically, which again is a very interesting thing we don't see in normal life. And finally, there's this phenomenon called uncertainty. Many of you may have heard of Heisenberg's uncertainty principle, which says that there are pairs of measurements that we can do in quantum mechanics where if we're more certain of the outcome of one of the measurements, then we're more uncertain of the outcome of the other measurement. So certainty with one hand means more uncertainty with the other hand. So in our everyday life, we kind of imagine that we can always get better and better confidence about the value of some physical thing just by doing more and more precise measurements on it. In quantum mechanics, this doesn't seem to be the case. We always have this kind of intrinsic uncertainty in the measurements that we do. And in quantum computing, the basic idea is to use all of these strange effects to our advantage, to use these phenomena to do things that we couldn't do without having access to these phenomena. And for the rest of the talk, I want to discuss what these applications are of quantum computers. The first one of these, which is a very important one, is simulation of quantum mechanical systems. So physicists tell us that the universe is based on quantum mechanics, on a very small scale especially. And so if we want to understand how the universe works, and we want to build things which take maximum advantage of what the universe has to offer, then we really need to understand quantum mechanics. But the problem is that on our standard computers, we don't know any way of doing this efficiently. If we want to simulate a quantum system on a standard computer, the best known algorithms for this are very inefficient. Whereas a quantum computer can simulate quantum systems very easily. It's one of the simplest things for it to do. And the sort of applications of these that people know now are things like designing more efficient materials and understanding things like solar energy better than we can now. So, for example, we might build better solar panels using this. Perhaps understanding superconductivity, the phenomenon of current flow without any apparent resistance, which might lead to kind of better energy transmission, storage, and so on, much more efficiently. Even understanding the natural world, for example, photosynthesis in plants. There's some evidence that this has some quantum mechanical component. So to understand how plants operate, we might need quantum computers to simulate what's going on in them. And finally, another important one is design of new medicines. So to understand how a drug works on the molecular scale, you really need to understand quantum mechanics. And quantum computers would let us do this very efficiently, would let us design new drugs and figure out how they work. And this would potentially be revolutionary to the pharmaceutical industry, I'd say. Okay, another very interesting problem, especially if you're a mathematician, is the problem of integer factorization. So this is a problem where we're given some number, like this very long number here starting 4358, and we're told that it's a product of two prime numbers, p and q, and we want to find out what p and q are. So if we're given p and q, then we can multiply them together to get their product. But if we want to go the other direction, it turns out it's really apparently much harder than this. And in fact, there's no efficient algorithm known to do this on a normal computer. But it's shown by Peter Shaw, who's shown there, that with a quantum computer we can solve this problem efficiently. So you might say, only a mathematician would care about this, but it turns out that the RSA public key crypto system, which is used all over the internet, is based around the hardness of this problem. So if we can factorize integers, then we can break this crypto system. So this obviously means that quantum computers are of great interest to people who care about security. Now, you might say that this is a slightly negative application of quantum computers, perhaps. It kind of takes away our security. But in fact, quantum mechanics can also help guarantee our security via quantum cryptography. So this is an idea where we use the laws of physics to guarantee the security of some cryptographic protocol. So we imagine that we've got two people, Alice and Bob, let's say, and they want to communicate. And they do this by sending photons from Alice to Bob. So these are the photons going along the communication line here. And it turns out that if we encode information in these photons in some clever way, and then if some eavesdropper, let's say Eve, comes along and tries to intercept Alice's communication to Bob, then Alice and Bob can detect that this has occurred. Using effectively this kind of these collapse and uncertainty principles in quantum mechanics, if Eve tries to measure the signal from Alice, then they can detect this and they can abort their protocol. So assuming that everything's implemented correctly with their protocol, they can guarantee that it's secure if they don't detect an eavesdropper. Okay. And the final application I want to mention is a very general application from computer science, which is unstructured search. So in this problem, we imagine that we've got some boxes. Each of them has a 0 or a 1 inside it. There's n of these boxes, and n is very big. And we imagine that we want to find a box that contains a 1. So if we look, some of the boxes have 0s, some of the boxes have 1s, and we want to find a box that contains a 1. But to start with, we don't know what's inside any of the boxes. So we want to do this with the minimum number of peaks inside the boxes. And it's kind of pretty intuitive that on with a kind of normal computer or kind of in a standard everyday kind of protocol, the best thing we can do is just kind of look inside the boxes one after the other, maybe starting at left and go to the right, or maybe picking them at random, something like this. And it's going to take us, if we have n boxes, about n queries to the boxes to find a 1, if, for example, there's 1, 1, and everything else is 0s. But kind of amazingly, there's a quantum algorithm, which is due to Love Grover, who's pictured there, which can solve this search problem with only about square root of n quantum queries to the boxes. So this is pretty amazing because it really seems that the computer doesn't have enough time to look into all of the boxes, and yet it's able to find a 1, even if there's only one in one of the boxes. Now, how would this actually be applied or used in practice? Well, it wouldn't be used to actually look inside kind of boxes physically, like I've illustrated here, but it would be used as an ingredient in some kind of unstructured search or optimization problem that we have to deal with. For example, we might have some problem where we need to satisfy a bunch of constraints, like, for example, some kind of timetabling or scheduling problem, and we want to find some solution to the problem that satisfies all of the constraints. And this algorithm would let us do this with only a square root of the amount of time that a naive algorithm would take to try every different possible solution to the constraints. Okay, so this is roughly speaking all I wanted to say. I wanted to allow a lot of time for questions afterwards. So just to summarise things I said, so quantum computers give us fundamentally new modes of information processing, which allow us to really implement some very exciting applications which we don't know how to do on a standard or classical computer. And these applications are driven by a different theory of physics to what's used by a standard computer, so it is really fundamentally different. So if we had a large-scale general-purpose quantum computer, then this would really make a big difference to all of our lives. I'm claiming just with some of these applications, such as cleaner energy or new medicines or more efficient energy transmission, anything like this could probably significantly impact our day-to-day existence. However, we don't actually have a large-scale general-purpose quantum computer yet. So people often ask at this point, when are we going to have one? And I guess different people in the field have very different takes on this, and maybe we'll hear Jack's take in a minute. Personally, I would be surprised if within, let's say, 5 to 10 years, we didn't see a quantum computer outperform a classical computer for some kind of perhaps slightly contrived problem where the quantum computer has a real significant advantage kind of from the start. And perhaps, I would say, kind of 10, 15 years perhaps beyond that, we'll really see quantum computers being used to solve problems that people really care about, of real practical interest. And if you're interested in learning more, I have a paper about a general kind of overview of quantum algorithms, which is kind of open access, so anyone can read it. And anything else you would like to know, please feel free to ask now. So that's everything I wanted to say, so thanks very much. Any questions?
With quantum states being unstable,
Yes.
if I factorise my prime number, how many times do I have to read the answer to actually get something that I believe is correct?
Right, that's a very good question, and actually there's two answers to that. So one answer is that indeed the quantum states that we need to produce to have a efficient quantum computer are quite kind of delicate and hard to deal with. So firstly, we need to have some very careful, delicate engineering to produce these things, which is one reason why it's so hard to do. But also we need to have this notion of quantum error correction, which is very important, which is that if we have some quantum information that is perhaps very delicate, we can preserve it over a long period of time. And people have already demonstrated some aspects of this, but there's still some way to go. The second answer is that many of these algorithms I talked about, such as the integer factorization algorithm, they do have a kind of probabilistic nature to them in that the algorithm might work or it might not work. And in the case of the factorization thing, the probability that the algorithm works is quite high, assuming that the quantum computer is fault tolerant and it works correctly and that kind of thing. If everything's working properly, then the probability the algorithm succeeds is, well, let's say 1/10 or something like this, and then you rerun it 10 times, and then you get the answer with quite high probability. So this doesn't significantly detract from the complexity of the algorithm.
So I think, I don't know much about this area, but I think a few years ago there was some question about whether there were going to be any gotchas and theoretically whether this was certain to happen. So it is pretty certain now, is it?
Right, so it depends. I mean, different people in the field have very different levels of optimism or pessimism, and there are people out there who are incurable skeptics who think that quantum computers will never work. But I think these people are kind of in the minority, and what we can say now is that there are no fundamental reasons why we think that it shouldn't work at building a quantum computer. Everything that we know points in the direction of it working, and the experiments that people are doing are getting bigger and bigger and more impressive. And although some of these things are very challenging, some of the experiments are very tough to do, they all point in the direction of things working and being scalable and going up to be bigger and bigger. So now I think for most people the question is like when, not if.
And all those examples have 4 qubits that you showed. Is that currently the kind of the top dog?
Right. So that's another interesting point. So people get really hung up on the number of qubits somehow. Like if you go to Wikipedia or whatever, there's some kind of timeline of the number of qubits that have been exhibited in different quantum computers. But really nowadays, I would say the more interesting thing is like the scalability and manufacturability of the technologies that people are using. Because if we have a technology that is fundamentally scalable, then there's no reason why we can't have hundreds or thousands of qubits. So, I mean, but to answer your question more specifically, I mean, people have got quantum computers which have, well, depending on how you count it, like maybe like 8 qubits, maybe 15 qubits, maybe something like this. But people have also demonstrated systems of much larger numbers of qubits, which maybe are not as controllable or not as precisely engineered. So at the moment it's kind of a trade-off between whether you want kind of precision or whether you want kind of scale. So, yeah.
What do you think D-Wave is selling at the moment?
Right, that's a very interesting question. I thought probably someone would ask about D-Wave. So D-Wave, just for those who haven't heard, are a company who claim to have the world's first large-scale quantum computer with, I think, over 1,000 qubits now. Quantum bits is what they claim. So there's two things to say about their system. Like, the first is that they're kind of taking a different approach where they're not trying to produce qubits that are so kind of precisely engineered and fault tolerant, but they're kind of really trying to scale up with a slight, like, if you like, sort of, well, this is maybe underselling what they've done, but perhaps a sort of quicker and dirtier approach where the you don't care so much about precision and fault tolerance on a small scale, but you really try and scale up very fast. Also, their system is not a general purpose quantum computer, so it can't run any of, in fact, the applications that I talked about today. What it does allow you to do is solve optimization problems using something called quantum annealing, and some of the optimization problems that they're targeting their machine at are indeed very interesting and very important practically. I would say that the jury's still out on whether they really will see a significant speed up based on their approach. So again, depending on whether you're an optimist or a pessimist about this, there are differing claims in the literature, and people sort of take different views. I feel at the moment, at least, it's fair to say that it hasn't been conclusively demonstrated that it can lead to a significant speed up over what you can do classically. And another one.
So I had a follow-up on that really, which is, so why is it so difficult for people to work out if these things are actually working or not? I mean, presumably you don't give them a problem unless you know what the answer is.
Right, so firstly, I mean, there are some problems where we do, we might find an answer which is not that easy to check. For example, the quantum simulation thing, let's say we have some quantum simulator that gives us some information about some molecule out. We may not be able to really know if that's the right thing. But some of the things, some of the problems like integer factorization, and also like some of these constraint satisfaction and optimization problems, like these ones are ones where we can check the answer. And that's true. So we can, for example, tell that the system is producing the right answer like 90% of the time. Maybe it produces something that's close to the right answer, 5% of the time, something like this. But what's much harder to tell is what the scaling is going to be like of the complexity of doing this over larger and larger problem sizes. So we can run some kind of experiments and we see, okay, great, the D-Wave machine or some other machine outperforms a classical machine on an input on a problem of size 100, but then eventually the problem size is going to be bigger than what we can put into our machine, and it's not always obvious whether this kind of level of performance will be maintained or what will happen exactly. So I don't know if that answers the question.
Is there some form of corruption when you're trying to extract the information from a quantum computer because of the uncertainty principle?
Yeah, so in general, when you have your quantum algorithm that you run on a quantum computer, you try and make it so that the answer is kind of as uncorrupted as possible, if you like. So you design the algorithm so that it should succeed with high probability. But this uncertainty principle and related things, they do really hamper your ability to use things like classical error correcting codes in your quantum computer. So you really need to use new techniques to deal with some of this stuff. So it does definitely come into that. Yes.
But two quick questions.
Mm-hmm.
Firstly, do you see this sort of thing, it's a hard problem at the moment, but 50 years down the road we'll have quantum computers and that'll be the normal thing to have? Or is it kind of, you'd have a big computer and that would do the quantum stuff, and then we'll carry on developing the traditional computers we have at the moment? And just to hark back to your communication with eavesdropping, is that kind of presuming an end-to-end system, which is never going to happen, really, unless you have an amazing quantum system which we can just implement and entangle everything.
Mm-hmm.
which seems possible but also very difficult as well. So I don't know. For me, in that one, you'll destroy, if quantum computers work really well, then you won't have any security, and by the time we have end-to-end quantum communication, then maybe, I mean, there's a big gap there, basically.
Right, I mean, these are both very interesting questions. So the first one, like, will we have quantum computers on our desks? So again, this is one where people really differ, but I would say first, the initial applications of quantum computing are much more likely to be, you know, the Googles and the Microsofts or whatever, having these things in data centers. And I think also you're never going to want a quantum computer to do your word processing or something like this. You know, some tasks we already have perfectly good computers for. But for me, I can see there really being some value in eventually having like a quantum processing unit in your computer which does the things that quantum computers can do. At the moment, you know, we haven't really, you know, explored the full scope of what the applications of quantum computers will be, and in particular, we haven't really explored kind of the consumer applications, which are the kind of things people might want to run. But in principle, I personally don't see a reason why we couldn't have this. So the second question about the quantum crypto, right? So it's true that the model has some kind of end-to-end nature in it, where you have, you know, this link that Alice and Bob have set up, and then you have this eavesdrop in the middle. However, you can have a network of more complicated things where, you know, Alice and Bob, you know, they both kind of talk to Charlie, who has has some kind of quantum, you know, data center thing where their links both terminate there, and you can have some kind of switching kind of capability where they can kind of talk to each other that way. So it's like they don't have to necessarily have a kind of physical link to each other. Although I should say that this hasn't really been demonstrated experimentally to the same extent that quantum cryptography has so far. And I mean, I should also say, you know, there are perfectly good classical cryptographic protocols for many of the things that we might want to do in terms of secure communication. But there are cases when quantum crypto, I believe, can give you a very interesting advantage, and I think that Jack may actually talk about some of this in his talk as well.
With conventional computing, we have, in fact, you can argue, predated the realization of the computers, a very strong theoretical model for what computers could do. I've not seen one for quantum computers. I mean, for example, the Turing machine relies on being able to copy information and read it precisely and write it precisely. Has anyone managed to produce any general theory of what a quantum computer can do?
Right, so it's very nice for me to have this question, because normally when people object about theory versus experiment in quantum computing, they object to the theory being ahead of experiment. So in fact, like the early days of quantum computing research, like people did think about this kind of thing. And for example, there is a quantum Turing machine model. People usually don't talk about it because it is kind of a theoretical thing, and it's unlikely to be how we'll actually build our quantum computers in practice. So we do have a model, and you know we can analyse things within that model, and all of the results I mentioned have some kind of rigorous underpinnings within this. On the other hand, people have had a lot longer with classical computers to study these things, and there are many open questions in quantum computing which you know have been resolved classically, or at least we have a much better understanding. For example, the limitations of quantum computers, we really don't know as much about this as we would like to. And this is something that people are working on, you know, every day now.
I think we'll move on. Thank you.
Thanks very much.
Great. Wonderful. Okay. Brilliant. How wide is the camera angle?
Pretty wide. You've
I stand on this side of the screen, potentially, on the corner.
Yeah,
Okay.
that's fine.
And let's put this guy in as well. Okay, my name is Jacques Carolan. I'm from the Centre for Quantum Photonics, which is up on the hill at the University of Bristol. And I'm going to talk to you a bit about how we actually intend to try and build a quantum computer. Okay, so we've heard from Ashley about the potential applications and things we can do with it, also how we can build it, the challenges that are involved in trying to build it, the kind of requirements that we will need to meet technologically to try and build it, and make some kind of predictions about where things are going. Okay, and I'll in particular talk about some of the experiments that we're doing in Bristol, but also talk more widely about that as well. Okay, so we've heard, nicely from Ashley about the kind of various applications of a quantum computer. Whether it's from doing computational tasks which you can't do with your classical machines. Okay, whether it's from doing some kind of quantum simulation, calculating ground states of molecules, designing new drugs, designing super efficient solar cells, things like that. Also, with quantum communication, you can do much more secure communication with quantum systems, and you can also do much more accurate sensing with quantum mechanics as well. I'm going to talk mostly about the first three and less about the sensing part. And it's really nice for me to come and give a talk and have Ashley come first, because it gives a kind of wonderful overview of what quantum computing is about. But often, if I really need to kind of understand something deeply, I often go to the kind of the Bible of quantum computing, which is the Daily Mail. And if you look under this article, they published on some of the work that we did under 6 pairs of flats every woman should own. They say, is the quantum iPhone around the corner? Okay, and in it they have the quote, and by 2025 quantum circuits might be everywhere, sitting inside laptops and phones, helping to design new drugs and smart materials, predicting the weather. Now, we don't believe that you can predict the weather with a quantum computer, because metrology, the study of measuring things, is not the same as meteorology, the study of atmospheric physics. Okay. Although I mentioned this to Ashley on the way over and made a joke about this, and it turns out he's actually invented an algorithm which could probably help you predict the weather. Okay, so yeah, that's worth noting. Okay, so I want to try and motivate and give a kind of tangible feeling for what are the type of speed-ups that we expect with a quantum computer. Okay, like really how much faster do we imagine this thing to be? Okay, so how much quicker is a quantum computer? So the questions we were looking at this problem of factoring, okay, breaking numbers up into 2 primes. Okay, so 21 is 7 times 3, for example. Okay, that's easy, right? That's an easy one to do. And it took my unoptimized classical computer about 1/10,000th of a second. They're running mathematics, so very unoptimized. I'm sure you could do it a couple of orders of magnitude quicker than that. Okay, how about this then? What are the prime factors of this? Anyone? No. Okay. So this is a 232-digit number, and this is actually the world record for classical factoring. Okay. And if anyone's worked it out by now, the answer is that. Okay. But it took a cluster of a few hundred classical computers about 2 years to calculate the prime factors. Okay. Now, if you could build a quantum computer which ran at the same clock speed as Mach, say gigahertz clock speed, I've done the calculations and I think it will take you about 10 seconds. Okay? So you've gone from 10 seconds to 2 years. So this is the kind of speed up that we're imagining with quantum systems. Okay? But so how much quicker? The answer is loads. Okay, it's loads quicker as a quantum computer. But there's a caveat with this, and as often the case, with grand, bold claims, is that this thing will require, well, in the absence of errors, which Ashley's already mentioned, about 4,000 quantum bits, okay, and 20 billion operations on those quantum bits. Now, if you add errors into the system and you need to error correct it, and I'll talk a bit about this more later, that number probably rises to somewhere between 1 and 10 million qubits. Okay, so that's a significant technical challenge. depending on how you count a qubit, we're probably at the regime of somewhere between, well, 14 qubits is probably the limit of what we can do classically. So how do we get there? How do we get to 10 million? How do we start scaling these things up? And that's what I want to try and explore now. Okay. So the first thing we need to understand when we talk about building a quantum computer is that information is physical. You need something physical to encode that information, right? So whether it's a cave painting that's 40,000 years old and the kind of the coloured chalk conveys that these people used to hunt bison, okay? Or whether it's a CD and you have 100 nanometer trenches on the underside which reflect a laser back and encode, the newest Justin Bieber song, or whether it's DNA, okay, the base sequence of nucleotides that inside all of us. I just want to make a little aside on this. That this photograph, which is a photograph of the European Bioinformatics Research Institute, was actually stored onto a piece of DNA and reproduced with perfect fidelity. Okay, so you can actually store things on DNA. Nothing to do with quantum mechanics, I just think it's kind of cool. And if we're going to talk about building quantum systems, okay, this is all the more relevant when we understand what we can do with our classical systems, right? So these are some pictures of the fin of a transistor. Look at the scale bar on this. This is 5 nanometers. Okay, a human hair, well, a nanometer is about 1/10,000th of a human hair. Okay, the smallest. So this thing is 5 nanometers across. Okay, this is something that humans make. Humans make something that is smaller than our smallest known virus. Okay, and I think that's amazing. So this is really the kind of scale where we expect quantum effects to happen. Okay. So how do we build a quantum computer? Well, we first want to understand, we want some kind of criteria. And luckily someone's come up with a criteria. This guy was David DiVincenzo, and he's kind of given us a recipe book of the things we're going to need to build a quantum computer. Okay. So first thing we need a quantum system. Okay, so a discrete 2-level system, right, which we can have as our kind of, say we've got an atom and it's got discretized energy levels, and you have your ground state, you call that a 0, and you have your first excited state and you call that your logical 1. Okay, or as we've already heard about, maybe using a photon. I'll speak more about that in a bit. So we have some kind of quantum system. Okay. We need to be able to initialize it. We want to start our computation somehow. Okay, so we're going to want to make sure we have enough control to put them all in some initialized 0 state. Next, we want to have it well isolated from the environment. Now, this is important because if your system isn't well isolated from the environment, you will lose information into the environment, especially if you can't control that environment. So you're going to lose information, you're going to have what's called decoherence. Okay? So it's very important that you can make your system well isolated. We need to be able to perform gates, we need to be able to turn 0s to 1s, 1 to 0s, jiggle things about, we need to have some knobs that we can turn with such to encode our actual computation. Okay? So you have some control over it. And finally, you want to be able to make measurements. Okay? You want to be able to ask this system questions. Are you a 0, are you a 1? And the outcome of that question is going to be encode the answer to our problem. Great. So, there are a number of different architectures that we could imagine trying to build a quantum computer. Okay, one of the most promising ones at the moment is superconducting circuits, where you actually build these electronic circuits, when you cool them down to millikelvin temperature, exhibit quantum effects such as quantized charge and flux around the system. Okay? So you can actually store your logical 0 and logical 1 on the way that charge moves around a circuit. You can also use trapped ions, so you get some charged particle, and then you trap it in an electromagnetic field, and by poking it with a laser, you can change it to 0, 1, and you can couple them to each other. And this actually is the kind of, what I would say is the world record for qubits. It's a 14-qubit system we've managed to manipulate. There's some awesome work to do at the moment with solid-state systems, where you actually dope things like silicon with an atom that you can individually address. And what I'm going to talk about is photons, storing information on single particles of light. Okay. So here's a picture of a photon. If you've never seen a photon, that's it there. And the neat thing about photons is that they're incredibly fast, right? From an information processing perspective, they move incredibly quickly, which is really nice. Okay. Secondly, they're incredibly easy to manipulate. We can basically take all of the physics we've known about since the 17th century to do with wave-like interference and apply that almost directly to the single photon level. Okay, so we know very well how to jiggle these things about. Okay. And secondly, this is a very low noise system. Okay, one way I can kind of prove this to you, and I'm going to borrow here from a professor, John Rarity at the research group. He says the lifetime of a photon is at least the age of the universe because the cosmic microwave background is still polarized. I think that's a fair statement. And if you want an explanation of why this is the case, well, photons move at the speed of light, and due to relativistic considerations, they don't experience time. And to kind of interact with something to decohere, you need to experience time. Okay. So anyway, whether you buy those arguments or not, they're incredibly low noise. So what we're going to do is we're going to store the photon, well, we're going to put the photon in one of two optical modes. You can imagine like a tunnel for the photon to go down. If it's in the top mode, the top tunnel, we're going to call that a logical 0. If it's the bottom one, we're going to call it a logical 1. Okay, so that's a way to initialize the system. Now we want to jiggle it about. Now we want to have some control over it. Turn zeros to ones, ones to zeros. How are we going to do that? It's actually relatively simple. We can build what's called an interferometer. And now you've already heard what a beam splitter is. It's a semi-silvered mirror. So if I put some light in there, okay, this is light's a wave, right? If I put light in there, and as it hits the first beam splitter, the amplitudes are going to split. So half's going to go in the top mode, half's going to go in the bottom mode. Now, if the path lengths on either side of the interferometer are exactly the same, these waves will be aligned. Okay? A peak matches with a peak and a trough with a trough. And you know what happens when we get something like that. You know, if you splash around in the sea or whatever, a big bit of wave adds up with another big bit of wave, and a small one with a low part with a low part. So you get constructive interference. So if you look what happens in the top mode, all the light comes out of the top mode. Okay, we see constructive interference. And what you can do is you can add some path length difference into this interferometer. And now when you put your light through it, you see that a peak matches with a trough. And we're going to get destructive interference, okay? High bit and low bit. They're going to cancel out one another. And what that means is that the light will then come out of the bottom mode. Okay? So the point is that if you can accurately control the path length in an interferometer, you can control your qubit. Okay? And I've actually built one here. So afterwards, I urge you to come up and look at it, and you can actually see the wave-like interference. And if I can build it in 2 hours, you can be assured that this is a very easy thing to do. Okay, and you look at it, and it takes up about this much of the box. Okay, so this is your single qubit processor, if you like.
So sorry, what manipulation is it doing? Is it a property of the property of the hardware that it does that, or is it switchable between the two functions?
It will be a property of the hardware. There's a number of ways you can do it. You might just have what you could do is just have a bit of glass which is going to slow the light physically down and just pop it in there. And in fact, that's effectively what we do when I'm going to talk about the chip experiment. So yeah, you're going to want to have some control over it. Absolutely. Okay, so this is how we do something with a single qubit. And I've told you that I've built a single qubit machine right here. Okay. But you can't see it from where you are, but it's about this big. That's pretty big. Okay, that's pretty big for a single qubit. I worked out if you wanted the full 10 million qubits, you need about 1 kilometer of floor space building something like this, which isn't completely insane, with like modern data centers. But trying to keep that thing aligned is going to be very hard. Your experiment is going to look like this. It's going to look like a mess, right? So, these are all big bits of metal and glass bolted to a 1-ton optical bench. And, this thing's meters in length. It's, it's bulky. It's unstable as soon as the temperature changes. This thing needs to be aligned on the wavelength of light. Okay, so it's a few hundred nanometers. And most importantly, this thing isn't mass producible. Okay, how do you go about producing 10 million of these guys? Okay, It's not straightforward. So what we've been pioneering in Bristol is designing and fabricating waveguide devices which actually guide the light down effectively tunnels on chip, okay, in a very compact manner, okay, in a very stable manner, and hopefully in actually a scalable manner. We can start scaling this thing up. So the way it works is that you have a high refractive index core, and what that means is that light moves slower through it, okay, surrounded by a lower refractive index cladding. Okay, and that effectively confines the light. And if that sounds familiar, it's because it's the basic operating principle of all fibre optics. Okay, that's how you confine light, total internal reflection. So we do that with these devices, and then we can realise quantum logic gates, beam splitters, actually on chip. And to do that, we bring the waveguides very close to one another, and the photon possesses some probability to quantum tunnel into the neighbouring waveguide. So that's effectively our quantum beam splitter on chip. And finally, we can also control it as well. This question, the point that you mentioned, how do we actually, what are our knobs that we turn on this device? Well, what we do is we lithographically pattern bits of metal on top of the circuit, which when you apply a voltage, heat the glass up, heat the silicon up. And what that means is it changes the properties of the glass, okay? And it changes how quickly light moves through it. So by judiciously kind of applying voltages, you can essentially manipulate your qubit. And I've actually, I'll mention this in a bit. So now we've got something which is completely stable, right? It's on a chunk of glass, yeah. We've got something which is compact, okay. This one is actually a pretty big one, 23 millimeters. I've got a variety of chips up here, which I will, which afterwards, please come up and have a look. And the silicon one, which is here, you can't see it because it's very, very small, okay? But it's probably, I guess, 1 millimeter long, okay? And it contains, I don't know, maybe 100 optical components on it, okay? So it's very, very compact. And now we've got something which is scalable. And what I mean by that is silicon provides the kind of bedrock of many huge industries in our societies today, right? The microelectronics industry, okay? Silicon Valley, essentially all integrated circuits use silicon as their substrate, right? And that's a, multi-billion-dollar business. Probably bigger than that, right? And the telecommunications industry, they deal with, manipulating light in silicon photonics. That's driven the telecommunications industry. Now, what that means is that we can use the expertise and the facilities of these industries. Okay, now, I'm not saying it's all plain sailing, and there are a number of technological challenges that need to be overcome so we can really apply their techniques to the single photon level, but the point is the infrastructure is there. We don't have to go about trying to build new fabrication facilities. Okay, and that is a really big selling point for quantum photonics. Okay, so we've got this cool platform now. What type of experiments do we want to try and do with this? Okay, so the first thing we can try and do is, factor numbers. So we did one of the first factoring experiments, and we showed that 15 is 3 times 5 with high probability. Now, yeah, sure, this is a proof of principle demonstration, but what this does is it shows that this quantum photonics platform is a viable platform. Okay, and we're looking to build from this. But it was an awesome demonstration. Okay, what more interesting, more exciting stuff can we do? So, what better way to look at this quantum simulation with a quote from Richard Feynman? How many of you guys are aware of Richard Feynman? Okay, a good amount of people. For those that aren't, I urge you to go and look him up. And there's some awesome videos of him on YouTube. Many great things about him. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem, because it doesn't look so easy. Okay. Nature at its most fundamental level is quantum mechanical. And if you want to describe it, the thing we're going to use better be quantum mechanical, right? I really like this, I think it's called an orrery, and it's this kind of mechanical system which uses gears, and you can actually simulate the orbital dynamics of our own solar system. Okay, so this is kind of what we're imagining with quantum simulators, purpose-built quantum devices which will be able to simulate things that we're interested in. Okay. and to kind of motivate this further, 35% of all British supercomputing power is spent, simulating the electronic structure of atoms and molecules, primarily for drug design. Okay, and this is part of the reason why it takes about $1 billion and about a decade to get a single drug to the market. Okay, so if you could use your quantum simulator, the hope is you could drastically reduce that. We've heard of heaps of examples of it anyway, protein folding, electrostructure problems, and also understanding photosynthesis, but like designing new materials. Okay, there's an endless number. So we've actually did one of the kind of early experiments where we calculated the ground state energy of a 2-atom system, helium hydride, on a quantum processor. Okay, and perhaps maybe the most interesting thing to look at is this, where we actually, you remember from GCSE chemistry, you have your canonical Leonard-Jones potential. It's a potential for 2 particles, two atoms, depending on how near they are, the potential, and we can actually calculate that with this chip. I think that's kind of cool. So, it's something you could still do classically, but it's a step along the way. And I'm going to take a very quick interlude and say that the chip that we have done that on, okay, is available for you to use on the internet. Okay? So if you go and Google quantum in the cloud, right, you'll go to the Centre for Quantum Photonics homepage, and you'll have access to a quantum simulator where you can, these are the waveguides and these are the kind of beam splitters on chip, where you can choose where you put your photons in, you can choose the temperature of the heaters to jiggle the photons about, and you can run you can do some tutorials and then run some experiments, and this is all in simulation. But when you come up with a good idea or you want to go and do it properly, we can actually give you time on the chip. Okay, and you can take some real data. So it's there for you to use, and there's a bunch of tutorials and stuff. So yeah, if you're interested in that, please use that. We've heard a bit about quantum communication as well. We imagine 2 parties that want to send a secret message to one another, right? Now, classically, you can never know if someone has been listening to it, because we can copy information in the classical world, but quantumly, we have some advantage over this, right? And the kind of reason why, we want to be able to tell if there is an eavesdropper there. Okay? And in the quantum world, when you look at something, you fundamentally disturb it. We can't get away from that, right? For you guys to look at me, particles of light are coming from that light, bouncing off me and into your retinas. Now, because I'm very big, it doesn't affect me. But if I was very small, okay, maybe the size of an atom or a molecule, that particle of light bouncing off me into your retina would affect me. Okay? So there's this disturbance which we can actually use to verify whether someone's listening to a channel or not. Okay? And also, I should note here, this is really the first commercially available quantum technology. Okay? You can buy these from a bunch of different companies. I think almost a decade ago, the first bank transfer was done using this. They even installed it in one of the World Cup stadiums for the South Africa World Cup in Durban, and did some kind of information transfer. And what we're looking at doing in Bristol is actually putting these devices onto mobile phones, so you can share some secure key with you and your bank. Okay, and perhaps this with our partners Nokia, and perhaps one of the most exciting things at the moment is there is a dark fibre network that runs under Bristol, and as part of the Quantum Communications Hub, which is a kind of nationwide kind of quantum partnership, we're actually developing a QKD network throughout Bristol. Okay, so there'll be a node up at the University of Bristol, there'll be one at Bristol, there will even be one in the watershed. Okay, and it will allow us to test new devices and new protocols on this system. Okay, so it's something awesome for Bristol. So where do we go from this? So in terms of photonics, we need to start scaling things up. We need to start getting more photons on chip. So to do this, we want to be able to produce photons on chip, and there's some great work which shows that we can use the properties of silicon to actually generate photons. We want to get larger circuits, and this is something that I've been involved with, the experiment on the top left. It's a very versatile quantum system. If you know what an FPGA is, it's kind of like a quantum photonic FPGA that we've developed. And finally, we want to be able to detect the photons on chip as well, and we're also doing this in Bristol. And hopefully with all this, we can beat a classical computer. A final thing I'm going to mention is they're actually thinking about how we're going to put these pieces together and build some large-scale quantum system. We've actually come up with a blueprint for this, so we're thinking about how it's all going to fit together. And the final thing I'm going to make some predictions. Is this going to be saved on the internet?
Yeah.
Okay, I'm going to make some tentative predictions. They actually align pretty well, actually, I think. I predict that in the near term, we're going to use a quantum system to beat a classical computer at something. Okay. Now, what I mean by that is not that we're going to have some large-scale 1,000-bit factoring machine with 10 million qubits. What I mean by that is we're going to have some non-universal analog quantum system which is designed for a very specific task. In terms of photonics, we think that at the regime of 10, maybe 15 photons, you can start doing things classical computers can't. I've personally been working on experiments with 6 photons, okay, so we're not that far away. There's some awesome experiments with large arrays of trapped charged particles, ions. You can maybe get 400 of them, which is super exciting as well. And some of this stuff to do with quantum annealing. So I think really in the past 1 or 2 years, we've started seeing a kind of turning point for quantum technologies in this sense. And I predict in 2 years we're going to do something a classical computer can't. And in the long term, I believe we'll have to have a universal quantum computation if we can suppress the errors. Okay, now errors is a really big problem for quantum computers. You can think of a classical computer, right, or the bits in the classical computer is a table with lots of coins on. And if you perturb one of the coins, well, gravity does a pretty good job of making sure the coins stay on the side you put them down. But in a quantum computer, because of quantum superposition, you really do care about the angle of that coin, and that means errors accumulate. Okay? And it was really the advances that were made in the kind of mid-1990s which showed that provided the error is below some threshold, you can still build a quantum computer. Okay? And there are some really exciting results over the past 1 or 2 years where people have started to demonstrate qubits that are actually, they have errors smaller than is required. Okay? So going from scaling, maybe 5 qubits up to tens of million might be very hard. Okay? But, all right, you can buy a terabyte hard drive for under 100 quid. Okay? That's 1 trillion things. You can buy 1 trillion things for less than £100. So is it completely insane to imagine that we can start scaling these qubits up? I don't necessarily think it is. And especially with recent, some of the kind of biggest technology on this planet have already started to have quantum computing, research programs. Okay, so I think because of this, it is possible that we will see universal quantum computation in our lifetime. So that's basically everything I wanted to say, and thanks for your time. Yes?
Are these things really quantum computers, or are they more sort of quantum circuits? Do you have anything that looks like classical computer in terms of being able to run programs, or are you just doing cascades of gates that give you an answer for whatever?
At the moment in photonics, if you want to, in the chemical simulation that I showed you where we found the ground state, that's actually an iterative algorithm. So you do pass through one gate, but we actually use that gate many times and build a kind of feedback loop. So in that sense, I guess, for me, it looks a bit like a computer. But that's only a 2-qubit machine. And trying to envisage a kind of 2-bit algorithm is maybe a bit hard to do. But I would argue there are heaps more interesting and cool stuff you can do with 2 quantum bits than you can do with 2 classical bits.
So you said, right, that if we are below a certain threshold of error, then we can sort of correct for that. Do you know in which implementations we have good enough control over our system so that we are below this threshold?
So over the past year, superconducting circuits have pretty much shown that, I think.
What about the other ones? Like
there's some awesome... Okay, so I guess there's 2 points here, right? So, can you make your qubit below error threshold, but can you scale it up and build loads of them? And now the ion trap guys have shown that, yeah, they can build really good qubits, but you've got maybe 6 lasers which you have to build. You can't buy these things off the shelf in some big trap, and the experiment is maybe half the size of this room. So that thing by itself isn't necessarily scalable. So I would say that the leading in terms of scalable architecture is probably superconducting circuits, but photonics is kind of on the brink of that, I think, because it's such a low noise system.
So what's the status like of the error correction for photonics implementations?
There have been error correction protocols demonstrated, but the protocols demonstrated are in large bulk optical systems like this thing is made of. So I would claim that those are kind of proof of principle showing that it's possible, but in a kind of on-chip scalable manner that hasn't been demonstrated yet and is a major goal for the field.
Within the photonic system, you've got a lot of kind of electrical gate manipulation. Are you kind of restricted by heating and cooling things to the speed of switching and the speed of therefore the system itself?
Yeah, that's a really good question. The experiments that I showed you actually do use heating, which is pretty slow. You can maybe heat at the kind of microsecond level if you're lucky. Okay, but that's pretty slow for the clock speed of a computer, right? There are a few other possibilities though, where we get the fast. Maybe you can use the fast switching that we already see in the telecommunications industry, doing things like doping of the system such that you can use different effects other than thermal. Electro-optic effect is one you might want to use, and then you could really get to gigahertz pretty straightforwardly. Now the problem is that introduces loss. It seems like the faster you go, the lossier system you get, and you want to make sure you don't lose your photons. So that is one of the big challenges for us at the moment.
Right.
Any questions?
Can I ask, maybe this is for you, and actually, the one of your points there was a near-term demonstration of a quantum superiority, or whatever you want to call it, outperforming a classical machine. In terms of, I don't know whether we should even call it a classical analog simulation. Like if I build an LC circuit or something that outputs a Fourier transform on an oscilloscope, are there not complicated signals that I could feed this thing where that circuit outputs the Fourier transform faster than any digital machine? And would you call that outperforming a classical machine? Like, do we even have ways to measure, like the computer scientists measure how fast like an analog circuit computes things?
Yeah. So, well, my understanding, actually, if I'm wrong, is that there are a number of examples of classical analog systems which can solve problems that we actually even believe to be in NP. But when you kind of sit down and do the maths, what you realise is that the errors actually blow up. Okay, while you think you're doing something, because we have to talk about things scaling. We have to talk about how things move in the long term. And what happens is these errors will ultimately cripple you. But for near-term demonstrations, you could probably do something rad. Something cool for that. I don't know if Ashley has anything to add to that.
Well, yeah, I mean, I guess all I'd say is like with these analog systems, like as you've identified, I guess kind of the interesting point is where you try and do something with your normal computer, you can't do it, and then you do it with your quantum analog machine, and then you can do it. And so I mean, to me, that shows that you outperform the classical computer quantumly. And in fact, I think, depending on your definition, we may already be at that point, because there have been experiments people have done which they haven't been able to interpret the results classically because it's just too hard for them to do the computation. But then the question is, how controllable are these experiments? Like how many kind of knobs can you twiddle on it? Is it really doing something that's kind of a computation, or is it just simulating itself? So it's kind of debate.
I've got a question from the YouTubes. From one of the guys in London. It's probably to you, Ashley. Is there any use of this sort of computing being used with neuroscience, neurology, neurosystems, or simulations of the brain, that sort of thing?
It's an interesting question. So, I know nothing about neuroscience, but as I understand it, it's still really a point of active debate. How much of a role quantum effects play in the brain. Could it be nothing? Could it be a little bit? Could it really be fundamental? I don't know. And what I would say is that if it turns out that quantum effects are important in understanding the brain, then quantum computers would probably be essential to to really addressing that in simulations and things. If it turns out quantum effects are irrelevant, it could still be that there's something you can do with a quantum computer, but as far as I know, no one's really looked at that. I mean, what could be more exciting than putting together kind of the brain and quantum computing? But I think no one has really done anything very concrete yet.
Right, cool. Do we need to leave time for people to come up to the front and just have a look?
Yeah. If anyone would like to come and see a single qubit processor, please, come up and I can show you some of the chips as well.
Yeah, so thanks. Everyone come up, not all at once. We're going to stop there, so thanks to both of our speakers tonight, Ashley and Jack. Any more questions, we'll have a couple more minutes here, but then we'll shoot next door so that we can clean the space up. Thanks.
Cool, yeah.
Come round with a screwdriver.
Yeah, exactly. You need a screwdriver. Yeah, it's maybe around.
I showed you that Mac